These robots can now form emotional bonds with you. Did artificial intelligence suddenly become smarter, or have we finally realized its limitations? Did reasoning models truly understand more, or have they simply learned to speak more coherently for longer periods? And perhaps more importantly, why have emotional robotic companions gone from being a matter of curiosity to something people actively buy, name, and build routines around? To answer these questions, we need to look at 2025 not as a year of flashy breakthroughs, but as a year of realizations. A year where the industry learned what works, what scales poorly, and what may fundamentally need to change. The most visible and widely discussed shift of 2025 was the rise of deep reasoning modes across nearly all major AI models. Throughout the year, companies rolled out systems capable of holding longer context windows, maintaining multi-step reasoning chains, and performing sustained analysis without immediately collapsing into inconsistency. Compared to previous generations, hallucinations decreased, logical structure improved, and models became significantly more reliable in domains like mathematics, structured reasoning, and software development. But this apparent leap in intelligence came with a cost that could no longer be hidden. These systems require unprecedented amounts of data, GPUs, specialized accelerators, energy, and physical infrastructure. Scaling intelligence meant scaling everything else at the same time. More parameters demanded more compute demanded more data centers demanded more electricity, more cooling, and ultimately more water. By the middle of 2025, a quiet consensus began to form across the industry. Brute force scaling is approaching its practical limits. Not because intelligence itself has reached a ceiling, but because the physical world is imposing constraints. Energy production is finite, suitable land is finite. Semiconductor manufacturing is slow, expensive, and geopolitically fragile. As a result, one of the most important questions of the year emerged. If scaling alone is no longer a sustainable strategy, what replaces it? This question pushed researchers toward alternative paradigms, and one of the most prominent among them was spatial intelligence. Researchers such as Fei-Fei Li, Yann LeCun, and teams at Meta emphasized models that understand space, motion, physical constraints, and cause and effect relationships in the real world. Spatial intelligence matters because today's AI systems still struggle outside text and images. For robots, games, and virtual worlds, understanding physics is not optional, it is foundational. Spatial AI directly feeds three major industries. First, gaming, where persistent and believable worlds depend on physical consistency. Second, virtual and augmented reality, where immersion collapses if the system does not respect spatial logic. And third, robotics, where failure to understand real-world physics leads to brittle machines that work only in controlled environments. At the infrastructure level, 2025 also introduced a shift in thinking that would have sounded unrealistic just a few years ago: space-based data centers. The logic is simple but radical. Orbit provides near-constant solar energy, fewer cooling challenges, and freedom from geographic and regulatory constraints. While still experimental, the fact that this idea is now being seriously discussed highlights how urgently the industry is searching for alternatives to earthbound limitations. Quantum computing followed a quieter but notable trajectory. Many researchers began comparing the current state of quantum computing to where AI models stood 5 years ago: powerful in theory, unstable in practice, and far from mass deployment. If this comparison holds, the next 5 years could bring dramatic acceleration, even if true general-purpose quantum computing remains distant. At the same time, the environmental cost of AI reached a level that could no longer be dismissed. Research published in 2025 estimated that AI systems consumed approximately 765 billion liters of water during the year. This figure exceeds the total global consumption of bottled water by humans. The associated carbon footprint approached that of a major metropolitan area. Cooling data centers and electricity generation remain the primary drivers, and with more than 11,500 data centers already operating worldwide, many of them expanding the trajectory points sharply upward. Against this backdrop of scale, constraint, and cost, a subtler but potentially more transformative shift took place. AI stopped being purely functional and began entering the emotional domain. AI-powered robotic pets became a legitimate consumer category. Companies like Ropet and Casio released devices that can see, hear, respond, and adapt over time. These machines do not simply execute commands. They develop apparent personalities, reinforce interaction patterns, and reward emotional engagement. Users report bonding, routine formation, and even feelings of responsibility despite knowing the entity is artificial. This is not a trivial development. Humans already form emotional attachments to static objects. When those objects respond, adapt, and appear to recognize us, the psychological boundary between real and artificial begins to erode. These robots may alleviate loneliness for children, elderly individuals, or people unwilling to take on the responsibility of real animals. At the same time, they risk normalizing isolation by replacing effortful human relationships with frictionless emotional feedback. Disney's autonomous Olaf robot demonstrates a parallel but distinct trend. Olaf does not engage in open-ended reasoning or conversation. Instead, through movement, timing, and physical embodiment, it generates genuine emotional response. Intelligence is not the product here, experience is. Storytelling, character continuity, and physical presence become the core value. To close out 2025, Andrej Karpathy offered one of the clearest and most grounded assessments of the year. He described 2025 as a breakpoint year for large language models. The most important shift, according to Karpathy, was the move away from pure human feedback toward verifiable rewards, particularly in domains like mathematics and programming. Models began discovering correctness rather than merely imitating preference. At the same time, AI revealed its uneven nature more clearly than ever before. In some contexts, models behaved like domain experts. In others, they resembled confused beginners. This inconsistency weakened trust in benchmarks. High scores no longer guaranteed real-world competence, and passing standardized tests proved insufficient as a measure of intelligence. Another defining change was the emergence of a new application layer. Tools focused on orchestration, managing context, coordinating multiple actions, and aligning outputs with human workflows proved more valuable than raw model improvements. AI moved out of the browser and into the operating system. It became local, persistent, and personal. Less a website, more a digital presence. Karpathy's final conclusion was direct. AI in 2025 was both smarter and dumber than expected, but undeniably useful. We are still exploiting only a fraction of its potential. As we move into 2026, the central question is no longer whether AI will advance, but how. Will progress come from new architectures, new training paradigms, deeper embodiment, or an entirely different way of thinking about intelligence itself? We will find out soon. Until the next episode, take care, and may the new year be guided by clarity rather than hype.